Hello everyone, welcome to our weekly revision class. My name is Fasika Imam. I'm a physics instructor at Labawi International Academy. In our today's discussion, we will focus on dynamics. Stay tuned. Dynamics is the field of physics that studies the motion of bodies and the forces that cause the motion. Last time, we have seen something about kinematics, and we defined that kinematics is a study of motion without reference to forces. So today, we will be focusing on the forces that explains why objects move. Sir Isaac Newton formulated 3 laws of motion and the universal law of gravitation in 1665, and these laws are the foundation of dynamics. A force is an interaction between 2 objects that results in a push or a pull, and forces are measured in units called newtons. And a force can cause an object to speed up, slow down, change direction, and change shape. And force is measured with a device called Newton meter. Basically, we have 2 types of forces that are called contact force and long range or non-contact force. When we say contact forces, the 2 objects that interact are in direct contact, whereas in long-range forces, the 2 objects interact at a distance. Let's look at some examples of contact forces. Tension, friction, normal force, and applied force can be taken as examples of contact forces. Gravity, electric force, and magnetic force are examples of long-range forces. Let us see Newton's first law of motion. Newton's first law of motion states that an object will remain at rest or constant velocity unless acted on by an unbalanced force. And this law is also known as the law of inertia. In other words, Newton's first law means if forces are balanced, then the object has constant velocity. If an object has constant velocity, then the forces are balanced. And this holds true for an object remains at rest. And forces are not needed for an object to maintain constant velocity. For instance, unbalanced forces cause the object to slow down and come to a rest. When the platform an object is traveling on suddenly stops, as shown on the screen, the object will continue to travel in the direction of motion until an unbalanced force such as a brick wall stops it. Newton's first law refers to the net force on an object. The net force is the vector sum of all forces acting on an object, and the net force on an object can be found by using methods for finding resultant vectors. As you can see on the screen, although several forces are acting on this car, the vector sum of the forces is 0. Thus, the net force is 0 and the car moves at constant velocity. Inertia. Inertia is a tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction. Newton's first law is often referred to as the law of inertia because it states that in the absence of a net force, a body will preserve its state of motion, and mass is the measure of inertia. The greater the mass, the greater the inertia of a body. Equilibrium. So equilibrium is a state in which the net force on an object is 0. Objects that are either at rest or moving with constant velocity are said to be in equilibrium. Newton's first law describes objects in equilibrium. To determine whether a body is in equilibrium, find the net force. If the net force is 0, the body is in equilibrium. If there is a net force, a second force equal and opposite to this net force will put the body in equilibrium, and we call this force equilibrant force. Let's look at the procedures that we should follow to draw the force diagrams. So, begin by identifying the object or objects you wish to analyze. We call this a system. Then, identify any long-range forces acting on the system. And in this case, since we are talking about mechanics, gravitational force should be taken into account. And then identify the contact forces acting on the system like normal force and frictional force. Then draw the forces as arrows in proper direction, with arrow lengths representing the magnitude of the force. Let's look at the following example about drawing force diagrams. So here we have an object lies motionless, meaning it is at rest or stationary. Then when we see the force diagram, we have two forces acting on this object, and instead of drawing the block, we take a point to represent this system, and this point is the center of mass of the block, and the forces are the normal force and the gravitational force. These both forces acts on the same object, so we can sum up and see that whether the net force is zero or not. So in this particular example, since the object is at rest, it is in equilibrium, there is no acceleration, therefore the net force must be zero, meaning the normal force and the gravitational force are equal and opposite. Let us see the second example. In this case, we have a suspended object or block, and it is connected with a string which is inextensible and very light as an assumption. So in this case, to draw the force diagram, we have two strings on the left and right hand side, and at the same time we have the weight of the block. So if we take the dot, which is a point of application of these forces, we can draw the direction of the forces in such a way as shown on the screen. The third example is ramp or inclined plane. So in this case, we have a block which is at rest on the ramp, meaning there are different forces acting on this block. So the first one is the weight of the block, which is gravitational force, which pulls the block toward the surface of the earth. The other one is there is a frictional force which keeps this object at rest. And there is a reaction force from the ramp towards the block, and that one is called normal force. Now, how can we solve balanced force problems? So in order to solve balanced force problems, you have to follow the following four major steps. The first one is draw a force diagram or a free body diagram, and then write upward force equivalent with downward force, and the left side force equivalent with the right side force, and the left side force equals with the right side force. And then identify the up, down, left and right components of forces. And then you can apply component method of vector addition to find the unknown values. So to support my idea, let's look at the following example. For instance, we have this system, and we assume that the system is in equilibrium, and we are asked to calculate the weight of this object as shown on the screen. So the first thing that we have to do here is let's draw the force diagram. So let's consider that we have three different strings. They are connected at one common point, and let's assume that this point is point of application of the forces. Therefore, we have a dot on the left hand side diagram, and that dot refers to point of application of the forces. Then this point is just pulled by three different forces in different directions. So we have Ft1, Ft2 and Fg. Then we have to resolve these forces into a known axis. For instance, we can clearly see that Ft1 can be resolved into x and y component, and then the x component of Ft1 will be equal to Ft2. Because we assume that the system is in equilibrium means the net force along the horizontal direction is zero. So keeping this in your mind, Ft1x is equal to Ft2, and Ft2 is given, which is 45 Newton. That means Ft1x is also equal to 45 Newton. Now, if you know Ft1x, then by applying trigonometry, we can calculate or we can find Ft1y and Ft1, because Ft1 is the vector sum of Ft1x and Ft1y. Remember, we want to find Fg or gravitational force, which is the weight of the object. So Fg is the same as Ft1y. Now, since we know the value of Ft1x, which is 45 Newton, and we have an angle of 70 degrees in this right angle triangle, we can apply tangent of 70 degrees, which is equal to opposite over adjacent, where the opposite side is Ft1y and the adjacent side is 45 Newton. Then we can crisscross and make Ft1y to be the subject of the formula, and therefore Ft1y will be 124 Newton. But mind you, the vertical component of Ft1 is the same as the weight of the object, because along the vertical direction the net force must be zero. And we have only these two forces, so these two forces should be equal and opposite. And hence the downward force or the weight of the object is also 124 Newton. So how big is Ft1? Now, we know Ft1x and Ft1y, so we can apply Pythagoras theorem to calculate this Ft1, or we can apply trigonometry to calculate Ft1. So if we take, for instance, cosine of 70 degree, it is equal to adjacent over hypotenuse, but the adjacent side is 45 Newton and the hypotenuse is Ft1, and then Ft1 will finally be 132 Newton. Let's come to Newton's second law of motion. Newton's second law of motion states that the rate of change in an object's velocity is directly proportional to the net force and inversely proportional to the object's mass. And the net force is dependent on the change of velocity or acceleration and mass of the object. Generally, we can state Newton's second law in such a way. So the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. Mathematically, we can rewrite this as the summation of all forces acting on an object is equal to mass times the acceleration of the object. So let's look at the difference between mass and weight. So mass is the amount of matter in an object and it is measured in kilograms, and the mass of an object is the same on the moon as on the earth. But weight is the force of gravity on an object, and weight is measured in newtons, and the weight of an object on the moon is about 1/6 that on the earth. And because of the difference in acceleration due to gravity, we might have different weight at different locations. And here we use a Newton meter to determine the weight of an object. And to calculate the force of gravity or the weight of an object, it is just defined as the product of mass times acceleration due to gravity. And for the Earth, the acceleration due to gravity is equal to 9.81 meter per second squared. Now, so let's look at normal force. The normal force acts on a surface in a direction perpendicular to the surface, and the normal force is not always opposite in direction to the force due to gravity. In the absence of other forces, the normal force is equal and opposite to the component of gravitational force that is perpendicular to the contact surface. And for an inclined plane where an object rests on it, the normal force is equal to mg cosine of theta. But on a flat surface, the normal force is equal to force due to gravity, which is normal force is equal to mu times mg. So normal force is equal to the weight of the object, which is mass times gravity. Frictional force. So frictional force is a force that opposes the relative motion of an object, and this frictional force is dependent on the normal force and the nature of the two surfaces. And friction is not dependent on surface area. When we look at friction in action, a car is able to move forwards due to the friction acting between its tires and the road. The force of friction of the road on the tire acts in the forward direction and is equal but in the opposite direction to the force of friction of the tire on the road. When a vehicle travels at a steady speed, the frictional force balances the driving force. And to calculate the frictional force, it is equal to mu times normal force, where mu is the coefficient of friction between the two surfaces. And basically, we have two major types of friction that are called static and kinetic friction. So, static friction is a force that resists the initiation of sliding motion between two surfaces that are in contact and at rest, whereas kinetic friction is the force that opposes the movement of two surfaces that are in contact and are sliding over each other. And kinetic friction is always less than the maximum static friction. In free body diagrams, the force of friction is always parallel to the surface of contact, and the force of kinetic friction is always opposite the direction of motion. To determine the direction of the force of static friction, use the principle of equilibrium. For an object in equilibrium, the frictional force must point in the direction that results in a net force of 0. And the quantity that expresses the dependence of frictional forces on the particular surface in contact is called the coefficient of friction. And to calculate coefficient of kinetic friction, it is equal to the frictional force divided by the normal force. And similarly, coefficient of static friction equals the maximum static friction divided by the normal force. So far, we have seen some major points about definition of dynamics, force, and Newton's laws of motion. Now, let's look at some applications of Newton's second law of motion. When you come to application of Newton's second law of motion, we already stated that the net force acting on an object is equal to mass times the acceleration of the object. Let's look at the following two examples. So the first one is inclined plane. So let's assume that we have a block which is moving down the plane. Then how can we apply the concept of this Newton's second law of motion, or how can we use Newton's second law of motion to define this motion of an object? So how can we apply Newton's second law of motion to define the motion of this block down the plane? So the first thing that we have to do here is we have to draw all the forces acting on the object. So here you can clearly see that the weight of the block is toward the surface of the earth, so it is in the downward direction, which is equal to m times g, and there is friction which resists the motion of the block. It is in the upward direction, which is up the plane, and we have to resolve this weight of an object into perpendicular and horizontal component to the plane or the ramp, so that the horizontal component of the weight is mg sin theta, and this mg sin theta pulls the block down the plane. But when you come to the perpendicular component of the weight of the object, it is mg cos theta, and this mg cos theta lets the block stick with the plane. But since the block just pushes the plane perpendicularly, there is a reaction force from the plane, and that is called normal. Now we know all the forces acting on the block. So for instance, if we apply Newton's second law of motion parallel to the plane, clearly you can see that there is a direction of motion down the plane, meaning mg sin theta is greater than the frictional force. To find the net force along that direction, you have to use mg sin theta minus the frictional force, and this net force equals mass times, here the acceleration is in the direction of motion. But along the perpendicular component to the plane, we have a normal force in the upward direction, and we have mg cos theta in the downward direction, and there is no acceleration along this perpendicular direction, meaning the normal force and the perpendicular component of weight of the object are equal. That means n minus mg cos theta equals 0. When we say n, it is the same as normal force. You can multiply this normal force by coefficient of friction. So coefficient of friction mu k times normal force, where normal force is mg times cos theta, will give you the frictional force. Now you can substitute this value into the first equation, which is mg sin theta minus frictional force equals ma. And finally, you will have mg sin theta minus mu mg cos theta equals ma. Now in all expressions we have common factor m, so we can cancel it out, and finally we will have acceleration of an object equals g into sin theta minus mu k cos theta. So we can apply Newton's second law of motion to calculate the acceleration of this moving object down the plane. When we see the second one, which is a pulley system, we have a single fixed pulley attached to a sailing, and there are two mass m1 and m2 connected with a string and hanged on this pulley. And as you can see on the screen, we have a motion directed downward on m2 side and upward on m1 side. So how can we apply Newton's second law of motion to calculate the acceleration of the system and the tension in a string? So let's assume that we have a frictionless pulley. Now first we have to separately treat each mass and draw free body diagram and know the number of forces acting on each mass. So for instance, for mass m1, there is a downward force which is m1g, that is the weight of the object, and in the upward direction we have tension on the string. So when we apply Newton's second law of motion, the sum of these two forces acting on m1 is equal to m1 times a. So since m1g is in the downward direction, we have negative value, which is minus m1g, plus tension because t is in upward direction. This will give us the net force, and it is equal to m1 times a. When we come to the second mass m2, similarly we have m2g and tension t acted on this object m2. Therefore, to find the resultant force, m2g is in the downward direction, so let's make it negative. But tension is in the upward direction, it is positive, so minus m2g plus tension equals m2a. But here the acceleration is in the downward direction, and therefore let's make it negative, which is minus m2a. Now we have two equations, equation 1 and equation 2. Now we can apply simultaneous equation, or we can sum up or substitute one into the other and rearrange this expression. And finally we will have minus m1g plus m2g equals m1a plus m2a. Now let's make a to be the subject of the formula. We can take out a as a common and divide both sides of the equation by m1 plus m2. And finally a, or the acceleration of the system, equals m2 minus m1 divided by m2 plus m1 times g. Now, by using back substitution in one of the two equations, you can find the tension in the string. and this tension equals 2m2 times m1 divided by m2 plus m1 times g. So following this technique, we can apply Newton's second law of motion to calculate the acceleration of the system, tension, coefficient of friction, and so on. Now let's look at one sample problem regarding friction. A student attached a rope to a 20 kg box of books, and he pulls with a force of 90 Newton at an angle of 30 degrees with horizontal. The coefficient of kinetic friction between the box and the sidewalk is 0.5. Find the acceleration of the box. So first let's plug out the given. The mass equals 20 kg and coefficient of kinetic friction is 0.5 and applied force is 90 Newton at an angle of 30 degrees above the horizontal. And we are asked to calculate the acceleration of the system. So here we have the box and there are 4 different forces act up on this box. So the normal force, the gravitational force, and the frictional force lie on a known axis. So the second step will be resolving the applied force into x and y axis. So the diagram on the right side shows the most convenient coordinate system because the only force to resolve into components is the applied force. So to resolve this force, the x component of applied force equals f times cosine of theta and the y component equals f times sine of theta. So the y component of the applied force equals 90 Newton times sine of 30 degrees, which is 45 Newton in the upward direction. And similarly, the applied force along the x direction equals 90 Newton times cosine of 30 degrees, which is about 77.9 Newton to the right direction. After this, we have to choose an equation to calculate the acceleration of the system. So first, let's find the normal. So to find the normal force, we have to apply equilibrium equation along the vertical direction because the box or the system is in equilibrium along the vertical direction. The sum of all forces along the vertical direction is 0. And once we use this and know the value of normal force, to calculate the frictional force, we can use coefficient of friction times normal force. And then if you know this horizontal frictional force, we can apply Newton's second law of motion along the horizontal direction to calculate the acceleration of the system in that direction. So to apply the condition of equilibrium in the vertical direction, you need to account for all of the forces in the y direction. That means the gravitational force, the normal force, and the vertical component of the applied force. And you know that the vertical component of the applied force and the normal force are along the vertical direction. So we can sum up and we have to make equivalent with the gravitational force. So the sum of this normal force and the vertical component of the applied force is equal to the gravitational force acting on the object. So meaning normal force plus the vertical component, which is F applied y minus gravitational force equals 0. So remember to pay attention to the direction of forces. So in this step, gravitational force is subtracted from the normal force and the applied force because this gravitational force is directed downward. And from this, you can rearrange and calculate the value of normal force, which is 151 Newton. As you all know, gravitational force is simply calculated by mass times acceleration due to gravity. Now, we already know the value of the normal force, therefore we can calculate the frictional force, which is coefficient of friction times normal force, and it is equal to 0.5 times 151 Newton, and it is equal to 75.5 Newton. After this, since we know all the unknown values, the only final unknown value is the acceleration of the object along the horizontal direction. Now let's apply Newton's second law of motion. And this Newton's second law of motion states that summation of all forces along the x direction is equal to mass of that object times acceleration of the object along the x direction. So in the horizontal direction, we have two forces that are the x component of the applied force and the frictional force. But these two forces are in opposite direction. So the applied force along the x direction minus frictional force is the net force. And this net force equals mass times acceleration along the horizontal direction. Now from this, if you make A to be the subject, acceleration along the horizontal direction equals the applied force along the x direction minus frictional force, value of A, which is equal to 0.12 meters per second square to the right direction. Let's come to Newton's third law of motion. Newton's third law of motion, sometimes called the law of action and reaction, and states that for every action there is an equal and opposite reaction. For example, a book is placed on a table and the book exerts a force due to gravity on the table, and an equal force is also exerted from the table to the book. and both forces are equal and opposite. So if two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1, and these two forces are opposite in direction. Because these forces coexist, either force can be called the action or the reaction. So forces always occur in pairs. Whenever two bodies interact, the forces they exert on each other are equal and opposite. Action and reaction pairs do not imply that the net force on either object is zero. The action-reaction forces are equal and opposite, but either object may still have a net force on it. Consider driving a nail into wood with a hammer. The force that the nail exerts on the hammer is equal and opposite to the force that the hammer exerts on the nail. But there is a net force acting on the nail, which drives the nail into the wood. Linear momentum. So momentum is defined as mass times velocity, and it is the measure of how hard to stop a moving object. And this momentum is represented by symbol P and is a vector quantity. So to calculate this linear momentum, it is equal to the product of mass and velocity in the direction of the velocity. Impulse. So impulse is the product of the force, the time over which the force acts on an object. And the impulse momentum theorem states that when a net force is applied to an object over a certain time interval, the force will cause change in the object's momentum. So generally, impulse is defined as force times time, or it is a change in linear momentum. So Newton's third law leads to conservation of momentum. So during collision, the force exerted on each bumper car causes a change in momentum for each car, and the total momentum is the same before and after collision. And we have two major types of collisions: elastic and inelastic collisions. Let's look at elastic collision. So a collision in which the total momentum and the total kinetic energy are conserved is called an elastic collision. Momentum and kinetic energy are conserved in elastic collision, meaning total momentum before collision equals total momentum after collision. So if we have two different mass moving with two different initial velocities, then m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final, meaning total momentum before collision equals total momentum after collision. Similarly, by using the second equation, which is half m1 v1 initial square plus half m2 v2 initial square equals half m1 v1 final square plus half m2 v2 final square, we can calculate whether the total kinetic energy is conserved or not. So let's look at the following example. A 0.5 kilogram ball is traveling east at a velocity of 9.5 meters per second when it collides with a 0.35 kilogram object traveling west at a velocity of 7 meters per second. After the collision, the 0.5 kilogram ball is traveling west at a velocity of 4 meters per second. What is the velocity of the 0.35 kilogram ball after collision? So let's draw the diagram. We have mass 1 and mass 2. So the mass, the initial velocity, is given for both of them, but they are in opposite direction. So for mass 1, we just show direction to the right side and we take v as positive, but for mass 2, we take v as negative. So when we multiply their corresponding mass and velocity, we can get their momentum. So momentum, initial momentum for mass 1, which is before collision, is 4.75 kilogram meter per second. And similarly, by using m times v, if you calculate the initial momentum of mass 2 before collision, it will be minus 2.45 kilogram meter per second. We have a minus sign because these two balls are moving in opposite direction. Then when we sum up these two momenta, then total momentum before collision will be 2.30 kilogram meter per second to the right direction. Now let's come to the second one, which is after collision. We have their mass and the final velocity of mass 1 is given, which is minus 4 meters per second because it directs towards west, so that we can calculate final momentum of mass 1, which is minus 2 kilogram meter per second. When you come to mass 2 after collision, we have its mass 0.35 kilogram, but we can find the value of P. Before collision, we know that total momentum is 2.30 kilogram meter per second, and after collision, the same value should be gained. And hence, since we know total momentum after collision, the sum of this final momentum of mass 1 and final momentum of mass 2 should be 2.30 kilogram meter per second. And due to this reason, we can deduct final momentum of second ball after collision, which is equal to 4.3 kilogram meter per second. After this, we can calculate the velocity of second ball after collision. That means V equals final momentum of second ball divided by mass of second ball. So we can divide P by M, and finally we will have 12 meters per second. Since we have positive value, it means that it directs towards east. The second type of collision is inelastic collision, and in particular, let's look at perfectly inelastic collision. A collision in which two objects stick together after colliding and move together as one mass is called a perfectly inelastic collision. And in this case, linear momentum is conserved, but kinetic energy is not conserved, meaning there is a loss of some amount of kinetic energy, and therefore total kinetic energy before collision is always greater than total kinetic energy after collision. Now, when we apply conservation of linear momentum, it says that m1 v1 initial plus m2 v2 initial equals m1 plus m2 times v final. Because in this case, we have common final velocity, and we assume that the two objects are moving together. Now, let's see one example related to this inelastic collision. So, a 2.1 times 10 to the power of 2 kilogram car is traveling east at a velocity of 52 km per hour and collides with a 3.1 times 10 to the power of 2 kilogram car traveling west at a velocity of 20 km per hour. During collision, both cars lock together. What is the velocity of the locked cars after collision? So, we can simply apply conservation of linear momentum. So, mass 1, initial velocity of mass 1 and momentum of mass 1 are given. Meaning, to calculate this initial momentum of mass 1 before collision, you can simply multiply m times v, which is m1 v1 initial, and it will be 10,920 km per hour. And for second mass, we have m2 and v2 initial, and therefore its momentum p2 initial will be minus 6,200 km per hour. In this case, we have the minus sign because mass 1 and mass 2 are in opposite direction. And to find total momentum before collision, we have to add these two momenta, and then the final value or final momentum before collision will be 4,720 km per hour. And after collision, these two masses stick together, so we can add their mass, and total mass will be 5.2 times 10 to the power of 2 kg. And the final momentum after collision is the same as final momentum before collision, and therefore it is equal to 4,720 km per hour. The only unknown here is the final common velocity of these two balls. Therefore, calculate this v, then v equals p over m, and we can substitute these values, and finally their common velocity equals 9.1 km per hour. I hope you enjoyed our lesson. That's all for today. Thank you.